Hi, I'm Beth Faber at the Hydrologic Engineering Center, and this is the sixth video of Lecture 2.1, the Basic Probability and Statistics Review. And in this segment, we'll talk about two topics, graphical probability distributions and also the metric long-term exceedance probability. This is where we are in our list of topics of discussion right near the bottom. We're almost finished. So graphical frequency curves. Not all random variables vary smoothly enough that they can be represented by one of the analytical probability distributions we looked at. Some distributions have to be graphical so they can capture the irregularities and some thresholds and discontinuities. Here's some examples. A stage frequency curve will see an abrupt change at the channel capacity with a flatter slope beyond as the floodplain gets wider. Another example, regulated flow frequency curves can have thresholds and flat spots at target flows and at channel capacity. So in these cases, we want to use a graphical curve. Graphical frequency curves have no equation, and so we have to work with them numerically. So here's an example of what could happen using a analytical distribution to represent a regulated flow. So this is, we see unregulated flows plotted in the hollow diamonds, and then the solid diamonds are some simulated regulated flows below a reservoir. So in this case, we have a reservoir in place to mitigate the flood flows. And we have a threshold down here at the bottom at, I think, a hydropower release, and then up here at the top with the large flows, we have them limited to channel capacity. So if we were to just fit an analytical distribution such as a log Pearson type 3 to this data, we would get this dark red line. So this doesn't capture well the threshold here, and it doesn't capture at all the threshold here. And if we were to continue this curve, the unregulated curve actually, the regulated red curve actually crosses above the unregulated curve, which wouldn't occur. So a better way to handle this is to fit in a green line like this, where we're smoothing some of the irregularities that are caused just by sampling error, but we're capturing the relevant thresholds. And the work isn't done here because we have to continue the curve out to where the regulated curve will eventually meet back up with the unregulated curve. So with a reservoir that is reducing flood flows, eventually the magnitude of the events gets large enough that the peak release will still equal the peak inflow. So we have to do some simulation and eventually plot out the point at which the regulated curve eventually meets the unregulated curve. Right? But in this case, an analytical probability distribution would not have represented this well at all. Okay, last topic is long-term exceedance probability. This might just be a hair more detail than your view of this topic yesterday. Or maybe not, we'll see. Okay. So long-term exceedance probability. So instead of considering only the annual exceedance probability of a certain outcome or the likelihood of something happening in any given year, long-term exceedance probability just lets us look over a longer period of time, because if you wait around for long enough, something extreme is more likely to occur. So long-term exceedance probability also will give us a slightly higher probability for something that will be a little bit easier to understand than the typically smaller annual exceedance probabilities. So let's consider this example. What is the probability that a house in the 1% or 100-year floodplain will be exceeded at least once in a 30-year period, typically the length of a mortgage? So let me adjust that just a little bit at the beginning. The location in the 1% floodplain that actually has a 1% likelihood is only the edge of the 1% floodplain, right? The likelihood is 1% at the edge, and then in all the area closer to the source of flooding, the likelihood of flooding is going to be higher. So this really should be worded, what's the likelihood that a house at the edge of the 1% floodplain will be flooded at least once in the 30-year floodplain, or in the 30-year period. So the first step, determine the probability of flooding in any 1 year. Well, that's going to be 1%. And next, applying the binomial distribution for the 30-year period. So the binomial distribution is defined as X number of successes in N trials. In this case, the success is a flood. So that's not an interpretation we want to share with our stakeholders, but it works in applying the binomial distribution. So X floods in N years. Okay, this first term of the equation is just the number of ways we can see X number of floods in n years. The next term is the probability of flooding in 1 year, taken to the power of how many years I need to see the flood. And then 1 minus p is the probability of not seeing a flood applied to the remainder of years in the record. Right? So for the probability of at least one exceedance in 30 years, I have to apply this formula for 1 success and for 2 successes and for 3 or 4 or 5 successes in n years. A way to simplify this a little bit is to start with the opposite. The probability of no exceedances in n years is easier to compute because it simplifies the equation. If x is 0, then the equation simplifies to this term goes to 1, this term goes to 1, and this term goes to 1 minus p to the n minus 0, so just 1 minus p to the n. So the probability of no exceedances in n years is just 1 minus p to the n. And then the opposite or complement of no exceedances in n years is at least 1 exceedance in n years, meaning 1 or 2 or 3 or more exceedances. And so since that's the complement, the probability of it is just going to be 1 minus the probability of no exceedances. So we have 1 minus p to the n. Right? For 1% flood and across 30 years, the probability is then going to be 0.26 or 26%. Right? That means we have a 1 in 4 chance of seeing the 100-year flood or 1% exceedance flood in any 30-year period. It's a larger and more understandable number to share to stakeholders and seems a little bit more relevant than just 1%. Here's a couple of other computations. The risk of 1 or more 10-year floods or 10% chance exceedance floods in 30 years is 96%. Now, if you consider that the 10-year flood is one that should be equaled or exceeded on average every 10 years, then actually the chance of going 30 years without seeing one is pretty small. So the chance of not seeing one is only 4%, and that makes sense. Let's instead look at a much larger flood with a smaller probability. So the risk of 1 or more 500-year floods or 0.2% chance exceedance floods in 30 years is 6%. Right? So our probability has gone from 0.2% in 1 year to 6% across 30 years. So again, a more understandable number. And then if we look at 50 years, which is the life cycle of some of our projects, the risk of 1 or more 100-year floods in 50 years is 40%. So that was our last topic, and here's a bit of a summary of all the things that we talked about in this lecture that was separated out into 6 videos. We revisited some probability concepts. We talked about estimating probability from understanding the system or from a data set. We used probability distributions to describe what's random and what's unknown. We fit probability distributions to data. We computed subsequent probabilities and frequency curves. And finally, we looked at long-term exceedance probability. So thank you for sticking with me through these lectures, and I will see you in the synchronous session to talk about the lecture and move on to the workshop. Thanks.